Group 16 elements. First element in group 16 is oxygen, followed by sulfur, then selenium, tellurium, then polonium. This group, like others, follow a magic number like 8, 16, 18, addition 34, 18 again, 52, then 32, 84. So 8, 18, 18, 32 is a magic numbers that we can remember to calculate the next element in the group. Sometimes group 16 elements are known as chalcogens, which mean ore forming. This is we call because many minerals do exist in the Earth's crust as ore in form of group 16 elements, combination compounds like sulfides, sulfates, oxides, even carbonates having a major chunk of oxygen in that. That's why they are calling chalcogen. General electronic configuration of group 16 elements is Ns2 and P4. It having 6 valence electrons. Oxygen forms a major chunk in Earth's crust. By mass, it is 46.6%, like silicon oxides and aluminum oxides. Many minerals having oxygen in that. And Earth's atmosphere contains 20.946% of oxygen by volume. We all know life is sustained on Earth by oxygen. Oxygen is used by most of the life on Earth for respiration. We have a different ores like gypsum, calcium ore, exists as calcium sulfate. Epsom salt of magnesium, this is a hydrated magnesium sulfate. Barite, which is a barium ore, barium sulfate is chemical composition, and many sulfides do exist, like for lead sulfide it's called galena, zinc sulfide is zinc blende, and for copper important ore is copper pyrites, copper iron sulfide is another ore. Let's talk about now properties of group 16 elements. From oxygen to polonium. Polonium is a radioactive element. First, let's talk about its covalent radii. We see here, as we go down the group, atomic radii systematically increases. That is because of the addition of new principal quantum numbers. We see here 3, then 4, 5, and 6 is keep on increasing. So addition of new shells is the reason for the increase in its radii. Further, we see a melting point. From first element, oxygen, the melting point is fairly low, 55 Kelvin, which is cryogenic temperature extremely low. But immediately next element, sulfur, having its melting point 393, which is above 100 degrees Celsius on normal temperature scale if we see. So why does such a difference do exist? Because oxygen exists as a diatomic molecule, O2, but sulfur exists as a polyatomic acid crown rings. Because of these polyatomic structures, they are having a higher melting points. Next is ionization enthalpy. Elements of group 16 elements have lower ionization enthalpy compared to group 15 elements. The reason is group 15 elements have extra stable half-filled p orbitals. Because of their half-filled electronic configuration, they got higher ionization enthalpy compared to group 16. Now, another property we see here, as you go down a group, ionization enthalpy keep on decreasing. The reason is, as the atomic number increases down the group, our atomic size increases too. So the electrons further and further away from the nucleus, and the electrostatic attractive force between the nucleus and the outermost electron is not that strong as in case of oxygen, which is fairly close to the nuclei. That is the reason our ionization enthalpy increases. Electron gain enthalpy. We see here, as oxygen have a very small size and it got a very high electron density. This is the reason when we try to add a new electron in it, that electron experiences a greater electronic repulsion forces. When we add a new electron, it experiences a great repulsive force from the electrons present. For the same reason, it has very low electron gain enthalpy compared to the other elements in group 16, only minus 141, which is the smallest in the whole group. So we have, this is the justification, electronic repulsion forces that do not allow the addition of another electron into oxygen with ease. Next is electronegativity. In terms of electronegativity, oxygen is only next to fluorine. I mean, it is the second most electronactive element in periodic table. Within the group, we see electronegativity will fall down the group. The reason is the same as the covalent radii. As size increases, the attractive force for the shared electrons in bonds, it reduces with increase in atomic number. Electronic configuration of group 16 elements reveal that they have a possibility of formation of -2 to +6 oxidation state. Oxygen, which is strongly electronegative as we know, it shows predominantly -2 oxidation state, like in water, but it also shows other oxidation states like -1, as in case of hydrogen peroxide. It also shows plus oxidation states in case of when it is bounded to more electronegative element, that is fluorine. So oxygen difluoride show +2 oxidation state for oxygen atoms. Sulphur, selenium and tellurium usually show +4 and +6 oxidation states in their compounds with oxygen and fluorine. Like sulfur tetrafluoride, we are having a sulfur hexafluoride. Then we are having a sulfur dioxide, sulfur trioxide, +4 and +6 oxidation states for sulfur. This is tellurium oxide with +4 oxidation state. The stability of +4 oxidation state increases as we go down a group. So it means when we move from oxygen to polonium side, we saw greater stability of heavier elements for +4 oxidation state like tellurium dioxide. It will be more stable compared to sulfur dioxide. The reason is ascribed to phenomena known as inert pair effect. What this phenomena is? It says s orbital electrons are reluctant to participate in reactions in tellurium. Another chemical properties of oxygen. Because we know oxygen do not have d orbital, so it limits the acceptance of electron by oxygen. For this reason, oxygen at best can make only 4 covalent bonds, which hardly do exist. Mostly it will do 2 covalent bonds using its 2 unpaired electrons. And most of the time these 2 paired electrons, these 2 pairs will remain unbonded, like in water. Reactivities. For group 16 elements, they form hydrides, like dihydride of sulfur, selenium, tellurium, polonium. And for these hydrides, we saw there is an increasing acidic character as we go down the group from oxygen to tellurium. This will be more acidic than water. H2S will be more acidic than water. Another property of group 16 is all the hydrides of group 16 except water, which is oxygen hydride, they possess reducing property, mean they act as reducing agents, and their reducing character increases down the group like acidic character. What is the reason? The reason is ease with which they can donate electrons to other species. The electron activity falls down the group, so their propensity to lose electron increases. That is the reason why their reducing nature increases. Another property is a bond angle. The bond angle of these hydrides also reduces down the group. The reason is same as we saw in case of ammonia. Bond length increases down the group. As a reason, the bond to lone pair repulsion reduces. As we go down the group, and this element and hydrogen bond length keep on increasing. So as these electron pairs, bonded electron pairs, are further and further from the central atom, in that case they can occupy closer positions to each other. Here we see it's a H2S. There, because they are very close to the sulfur, their repulsive forces are greater, bond pair repulsions will be greater. They try to occupy further away positions. But in next, selenium, bonds are further and further apart, bond pairs are further, so they can come a bit closer because repulsive electrons are not that close to the atom. Going further to tellurium, it is further away. Bond pair will be further away from this atom, by our group 16 atom. That is the reason they can afford to come closer further. The reduced bond pair repulsions are responsible for reduced bond angle. Now further, all these elements react within oxygen, which is also an element of group 16, to make oxides. We are having a sulfur oxide, selenium oxide, tellurium oxide, and polonium oxides. And stability of dioxides increases down the group due to inert pair effect we just discussed previously. Here we are having a sulfur dioxide. Sulfur dioxide acts as reducing agent, meaning it can oxidize itself further to +6 oxidation state. As the reason is S having a 3d orbitals to extend its octet that allows it to accept or lose electrons or accept the ligands from other elements. Stability of the halogen compounds of group 16. These halides, their stability reduces from fluoride to iodide. So fluoride are the most stable halides for group 16 elements, and iodides are least stable halides of group 16. As the size of anion increases, bond strength reduces. So reduced bond strength is responsible for lower stability, meaning those compounds are easy to break. Among these, SF4, which is tetrafluoride, is a gas, selenium tetrafluoride is a liquid, and tellurium tetrafluoride is a solid. Here we see sulfur tetrafluoride structure. It got some sort of distorted bipyramidal structure, also known as a seesaw geometry. It's sp3p hybridized, and one position among these hybridized orbitals is occupied by lone pairs. The monohalides, which are diameric in nature, like SF, this is nothing but a diameric halide, SF, S2S H2Cl, and H2Br2. They are fairly reactive and undergo disproportionation to acquire more stable oxidation states. Like selenium dichloride, it makes selenium element, which is zero oxidation state. So from here it goes in +1, it got reduced, and selenium makes a tetrachloride, which is oxidized to acquire both are stable oxidation states as a result of disproportionation of these monohalides. There goes to disproportionation, we know. And among these hybridized geometry of H2O is sp3, having a 2 lone pair that have been utilized for hybridization. It got a bend shape. SF2 is also sp3 hybridized. SL2, it uses 2 lone pairs. SBr2 also uses 2 lone pairs for hybridization. Dioxygen properties. First of all, in In many places in lab scales, this can be prepared from using our potassium chlorides. This is hypochlorite. Potassium hypochlorite, when heated with manganese dioxide, gives us potassium chloride and oxygen. Another way is using silver oxide and mercuric oxides. On heating, they decomposes to give us oxygen. These are other way we can see our storage of oxygens, which applying energy we can recover oxygen from the elements or compounds. Let's talk about certain compounds of oxygen like hydrogen peroxide. It will be interesting for you to see that many jetpacks that we see are used for adventure sports are based on hydrogen peroxide. Hydrogen peroxide decomposes violently into water and oxygen using a catalyst like finely divided metals, silver or manganese dioxide. This is a jetpack. Here, pure H2O2 will contain it. Then it is passed through these reactor chambers. It decomposes violently, and the steam and oxygen produced will be funneled through one array to give us a push or a propulsion. This is what you see here, jetman using this hydrogen peroxide. That's what happens. It decomposes to give us water and oxygen. Among the other properties is the solubility of oxygen in water, which is to the extent of roughly 3% or 3.08 centimeter cube in 100 centimeter cube of water at 20 degrees Celsius. Now this solubility of oxygen in water is very important for marine and aquatic life. We see 10 to 15 parts per million in fresh water and 8 to 11 ppm in seawater, which supports the water aquatic life.